And the idea was I was going to give you like this grab bag of various UTXO set proposals or ideas. And the first one was this trust-free light nodes that first appeared on Bitcoin Talk in 2012. Also going to talk about, very briefly, about Peter Todd's Merkle Mountain Range Commitments proposal, Brown Cohen's TXO bit field, and the role of UTXO set hashes. So trust-free light nodes was proposed in a Bitcoin Talk post way back, 2012, and Alan says, use a special tree data structure to organize all unspent TX outs on the network. You can see this is quite old because he doesn't use the word UTXOs. This is before we even used UTXOs, I guess. And use the root of this tree to communicate its signature, he means commitment, between nodes. The leaves of this tree actually correspond to addressed scripts, and the data at the leaf is actually a root of the unspent, of the UTXO list for that address script. To maintain security of the tree signatures, it will be included in the header of an alternate blockchain, which will be secured by merge mining. So that's merge mined. I don't want to go into what that commitment is, but the idea is instead of storing the entire set of data, you store some commitment to that set. And then when someone wants to use something from that set, they give you a proof.
Maybe merge mining, explaining a bit what.
I don't really know much about merge mining. Maybe Felix knows because he's been around forever.
I mean, there was this idea to build on Bitcoin security and have miners basically mine or commit other chains into the header or into the, like we do now with SegWit, and have an anchor for these other chains but and then the other way you could also if you had like faster block times on the other chain, I think so if that's the case, I think maybe for Dogecoin or something, which is now merged by Litecoin, you would have two different valid headers. So what, for instance, the smaller chain, the Dogecoin chain, would have a valid header if it was committed into a Litecoin header that was pointing to, wait.
So you can commit a merge mine block into Bitcoin headers.
Yeah.
Yeah.
And you can actually set the difficulty of the merge mine chain to be higher. So no, you might make a commitment every block, but the commitment is only valid if the actual Bitcoin block has a difficulty which is as high as the one that is in your mined merge mine chain. So you have to maintain two parallel data structures in your.
Yeah, but I mean, it means as a full node, you have to validate both consensus.
That's correct.
Yeah, that's why it fell off, because
it's a little bit
then
like
sidechains came, which gives the same sort of security without hard fork in the network. But then we also have sidechains.
The sidechains we have today only work with federated sidechains.
Yeah,
we don't have any like mining.
We had, but Luke broke one. There was a big sidechain that was a long time ago, and Luke broke it. And now we only have with federated because we know it's possible to break.
I know a few mining pools. I think F2 pool still merge mines main coin with Bitcoin. Yeah, I mean it's there's so many. There was mentioned so many times to like anchor. It was like never really materialized.
So I mentioned earlier on Monday that there's lots of discussion about what that structure should be, and in general, I think that's what a lot of the conversation is. If we want to create some kind of commitment to a UTXO set, like how do we do that in an efficient way that's easy to update, easy to produce proofs for, and easy to verify proofs for. So the light clients in this model would store the root of that structure, so the commitments, and then be given proofs of inclusion or proofs of exclusion for their outputs. You just download a UTXO set from somewhere, and because this is committed by the miner, or because it's committed in this alt chain, You check using the latest block that it's valid. And then eventually the discussion goes on over many pages of Bitcoin talk and evolves towards the root being a commitment, much like SegWit, the SegWit witness Merkle root being a commitment in the coin case. So let's have a look at that. Where is it? Yeah, Greg Maxwell says an alt chain is probably the wrong way to think of this. It's committed data. There doesn't need to be a chain. So you can just put it in a block. Around the same time, Peter Wooler implemented UltraPrune. So this is a really important change in the way Bitcoin Core was structured, because before this we stored the entire blockchain. And so if you wanted to run a full node, you'd need the entire blockchain because you're looking at that data structure the whole time. This introduced the concept of a UTXO set, or it instantiated the concept of a UTXO set and made it the chain state. And he says block pruning itself is not yet implemented, but this makes it trivial to do so, because now you can just get rid of that block data. Now with this, with UltraPrune, you now have a UTXO set, so you could potentially start exploring these ideas of creating commitments to that set, or having to assume UTXO or whatever. And then Peter says in this thread, we now do keep an explicit set of UTXOs. I'll make that bigger for you. But indexed by TXID without explicit tree structure or authentication. It only keeps the current active UTXO state, and no effort is done to keep older trees available by sharing subtrees. Keeping full snapshots of older trees is a bad idea in my opinion, and re-rolling the entire history even more so. But on-disk files with data to undo the applications of blocks to the UTXO are an easy solution. So if we see UTXO as this important piece of data that we need consensus on, a block is a patch to that set, right? It adds some things and deletes some things. So if we have the UTXO data and we have the .rev files, the undo data, and we commit to the undo data and we commit to the UTXO set, then we can arbitrarily move forwards and backwards through the blockchain just by taking a snapshot and finding those patterns. So he says, if the block headers commit to the hash of these undo files as well as the Merkle root of the current UTXO state, clients could ask their peers for backward movement data, which is enough to release a client stuck in a sidechain. So a sidechain in this case is like a branch here, without transferring the entire UTXO state. I see no reason for not doing this. So that's maybe optimistic. People thought about things differently back then, I guess, but making that commitment to consensus rule would be a soft fork, obviously.
Question for you. What's in the undo data that's not in the blocks?
Okay. So a block contains all of the new transactions,
Right.
and it contains references to the outputs that you're spending.
Okay.
Right, but it doesn't contain those outputs. So if you want to undo that block, you need to remove the new coins that have been created, the new transactions, and you also need to re-add the coins that have been spent. But you don't have that in the block data; it's further back in the blockchain. So the undo file gives you that data. It tells you which coins were removed in that block.
It's a reference from the current UTXO to the spent.
Yeah, so if you think about a transaction in the block, the inputs are an out point, right? It points to a TXID and an index. And if you want to undo the result of that, you need to know what that coin was that was spent. Is there anything else in there, Felix? I think that's it, right? Felix is the .rev master. He knows everything about undo files.
Yeah, I rediscovered it recently how awesome it is to do so, because you can't even if you have a block, you get raw block, you can't even see the fees of the transactions of a mine block, and but you can if you have the TX index enabled, you can do lookups for each of the out points and then find out how much money there was in there, and then calculate the difference. But that's a lot of lookups. So the easy way is just like you load the block, and you load for the same block the undo file, and now you can just like fill in that all in like pretty much like one operation, and do fee calculation on the block, or even like so a lot of block explorers don't. If you ask for transactions, they don't show you what the from address. Sorry for that word. I know some people get offended. But you can now with the undo data, because that is like the script is stored there. I mean, it's pretty much just what was the script and what was the value. And I think now with the since 15 we only store the height of when that output was created. So you can do also calculations like
and whether it's a Coinbase output.
And what is Coinbase, and that allows you to calculate funny things like Coinbase destroyed on a block if you fancy that, or another thing is you can look up like for a block you can fetch some statistics like how many how old is the median coin that before it gets destroyed again. And I think 50% of the coins that get created in a block gets destroyed within the same block. And I think if you expand that to like an hour or two, I think you go up to like 30%. So it's coins are a lot of coins are very short-lived, and then you have it's very distribution, right?
So I can do fee estimation because I just look at the diff of the transactions that were removed, and then I only have to do lookups on those, right? That's the idea. Is that correct?
To calculate what the fee was, so you know only the fee that are for transactions in your mempool right now.
Correct, but was your idea? I think you mentioned by looking at the transactions, look at the reverse. What do you call it? The ref.
Sure.
Yeah,
Either ref file or undo block files.
Yeah, let's talk about how great red files are after this. Okay, so that was Trust-Free Light Nodes back in 2012. So these ideas have been around for a long time. The underlying idea hasn't really changed, right? How do you run a full node trustlessly without storing this huge amount of data, which now I think is around 3.8 gig for the UTXO set. One suggested construction was from Peter Todd, called Merkle Mountain Ranges, and this construction is deterministic, indexable, and insertion ordered. And new items can be cheaply appended to the tree. Once they're added, they're never removed, just updated in place, and the proofs are log n size. What's nice about the fact that nothing's ever removed is that I think should be easy to update proofs for items in this structure.
This is used in Grid. Grid uses an
I don't know.
Yeah.
Merkle Mountain range for their outputs.
Okay, I didn't know that. So I'll pull out a few quotes from his mailing list post. He says a hard upper limit on UTXO set size could create a more level playing field in the form of fixed minimum requirements to run a performant Bitcoin node, and made the issue of UTXO spam less important. So the Merkle tree commits to the state of all transaction outputs, both spent and unspent. We can provide a method of compactly proving the current state of an output, so you can both prove that it exists and also prove that it's been spent. So lets us archive less frequently accessed parts of the UTXO set, allowing full nodes to discard the associated data, still providing a mechanism to spend those archived outputs by proving to those nodes that the outputs are in fact unspent. So this is kind of linked in, I guess, with what Felix was saying about the age of coins, coin spent age. We see that very strong Pareto distribution where coins that were created more recently are far more likely to be spent. So if we make that kind of hot and older coins cold, we access those hotter coins more frequently. So we make the proofs for those ones shorter.
It's also touching the what Luciano was talking about, the TX cache view, case of cache view. It's the same idea there.
And then there's he goes through the implementation there, the construction, which I'm not going to do.
So it's the wanting to make these proofs grow logarithmically in the number of UTXOs ever created, ever in the history of Bitcoin. That sounds like good.
I think so, yes, for old ones. Yeah. The idea is very old coins very seldom get spent. He sent a post to the mailing list, I think a few weeks or months later, saying that these commitments shouldn't be implemented as a consensus rule, they can just be shared on the peer-to-peer network. And he argues that a snapshot without an attestation from known individuals, a snapshot with an attestation from known individuals that you trust is a better security model than having miners attest to validity. So you can do interesting things with this without changing consensus.
Did he say that in the context of minor centralization? Or?
Yeah, I think so. There's a concern that if miners are committing to this data, we might kind of implicitly move to a model where we're trusting miners.
But it's the way you can validate.
You could validate it, but if the de facto becomes that you are using this commitment from the miners, then people stop being so concerned about the cost of doing a full validation. And it might eventually become impossible, like people argue that Ethereum is really impossible to fully validate because you can't catch up with the tip. You want to avoid that in Bitcoin. Next up I'm going to talk about UHS, which is a proposal that Corey sent to the mailing list about a year ago. And I'm going to go back to Graham Cohen's proposal after this, but I think this is a really nice write-up because he talks about why do we have a UTXO set at all? And there are two reasons. One, we want to know what coins exist, and two, we want to know how they can be spent. So we can separate those two functions, and that's what he's doing here. So we keep a set of the hashes of all the UTXOs, and we mark, we add to that set when new UTXO is created, and we remove from that set when it's removed. And it's then the responsibility of the party spending that coin to give us a pre-image of that hash. So our UTXO set goes from being this structured data to being these commitments. This is not a UTXO set commitment scheme. This is just a different way of storing our UTXO set. He gives us some figures here. So the UTXO disk space when he sent this was 2.8 gig, and if we just store these hashes and get our peers to give us the pre-image, then we can reduce that to 1.6. It's quite nice. And again, this is all just on the peer-to-peer network, so there are no consensus changes. Any questions about that one? I recommend this mailing list post. It's very clearly written. And the important thing here is the burden of holding UTXO data is technically shifted from the verifiers to the spender. So this is a really important consideration in all of these proposals. Like, where does the cost lie? And currently, with the full node, the cost lies with the node operator. You might say that's incentive incompatible. And schemes like this remove the cost of storing and sending this data from the node operator to the wallet.
How do you make sure that the hash matches with the script of commitment?
So you keep a set of all of the hashes, and when someone wants to spend a UTXO, they provide you the UTXO, you hash it, look up in your set, and if it exists, and they're spending something that exists, and then you remove it from your set.
So the hash is not the, so it is the hash of the commitment script? specific.
It is, so for each new output, gather all the extra data that will be needed for verification when spending it later. So the amount, script public key creation, height, Coinbaseness, and output type. And then that's all hashed
Okay.
together.
So new data structure.
Okay. So the next one I wanted to talk about was TXO bit field from Chaincode. And this again uses that concept of the difference between UTXO set being a set where we are checking for existence and the actual data needed to verify valid spends. So for this one, all of the outputs in a new block are given an index, and they're then, I guess, you put them into a Merkle tree, and the proof that they exist is, or when you want to spend them, you give the Merkle proof, so that reveals what the UTXO is, and the node operator simply keeps a bit field of all of the outputs in that block set to 1 when the block is created, and whenever something is spent, flip it to 0. Right, so by looking at the Merkle path field given with the UTXO or the spend, you look down, you look in your bit field and you say, has this already been spent? Yes, this is invalid because you're trying to double spend. No, fine, you can spend it. So this is linear with the size of the blockchain in terms of the outputs, but it's 1 bit per output. And so that 256 x constant size factor is quite important. Storing 1 bit per every output ever being created is not huge. And it becomes sparse over time, so it's almost all zeros, and that can be compacted and compressed pretty nicely. The really nice thing about this, unlike some of the other schemes, is that because the position is constant once the block's been mined, that proof stays constant. With a lot of other schemes, like accumulator schemes or Merkle mountain ranges or whatever, whenever that commitment changes for a new block, then the proof changes for every output. And that's quite a high cost for the wallet. So imagine I have an output that I want to spend, I keep a proof showing that it exists, a new block gets mined, I need to update my proof. And I need to do that for every block. Because this is constant, you don't have to do that. Any questions about that one?
So there's a bit set per block. So that how it works.
Yeah, well, I mean, they can just be, I guess, per block, but when you store them on disk, you could just, I guess, push them together and have indexes into where the blocks are.
Kind of like the compact block filters, kind of sounds similar. A little bit. There's 1 filter per block, sort of.
Well, this is a bit field, so it's a bit different. All right. The last one I wanted to talk about was Peter Willer's rolling UTXO set hashes. This is not a proposed change to consensus or even to how we store UTXOs, as I mentioned on Monday. I think this paragraph is pretty good because it points back to a lot of the other things I covered. Much has been written on the topic of various data structures and derived hashes for the UTXO or TXO set before, including the trust-free light nodes, MMR commitments, and TXO bit field. They all provide interesting extra functionality or trade-offs but require invasive changes to the P2P protocol or how wallets work, or force nodes to maintain their database in a normative fashion. Instead, here I focus on an efficient hash that supports nothing but comparing 2 UTXO sets. However, it is not incompatible with any of those other approaches, so we can gain some of the advantages of the UTXO hash without adopting something that may be incompatible with future protocol enhancements. So a more modest.
And then what do you do with this hash?
Well, he suggests a few use cases. We currently have this RPC, get TX out set info, which I think just concatenates all of the UTXOs and gives you a hash of that. is quite slow and expensive because it's done on demand. I think it can take several minutes. If you had a rolling hash commitment, you'd do it in the background as the tip advances, and so you could get, for the tip, you could instantly get that hash.
And then use it for like assume UTXO or something like
You
that?
could use it for assume UTXO. So yeah, assisting in implementation of fast sync methods with known good blocks, UTXO sets, and also a consistency check. So
There is a hash serialized underscore 2. Is that the new one, or is that just
You can then add this hash as a commitment to the Coinbase transaction or something like that.
you potentially could, yes. Yeah. That is a big debate whether that's desirable and how we would do
Yeah, it will make like it will lower the amount of full nodes even more.
it potentially. Yeah.
So how is this hash calculated?
So he in this mailing list post he gives 2 potential ways of doing it, and then I've added a third which is more recent than that mailing list post. One is this Bel Air Chaincode paper, which gives 3 suggested designs. One called X hash, which hashes every item in the set and then XORs them, which is completely insecure from the birthday attack. One is add hash, which hashes every item in the set and then adds some modulo some large number. Again, insecure, not quite so trivially. And then the one that actually might be secure is mu hash, where you hash everything and multiply it modulo some number. So that's one way of doing it. Another way would be to, so here's the birthday, this is quite a seminal paper for Bitcoiners. Another way is to hash onto the curve, and we know that curve operations are homomorphic under addition, so you can take your set, hash every item onto the curve, add them together, doesn't matter which order you did that. And this is a paper that describes how to do that with some binary elliptic curve.
Can you also remove?
Yes, you remove by
like,
taking the negative. Yeah.
I'm trying to pinpoint what are they trying to solve exactly with these different hashes. Are they trying to solve the problem of sorting the UTXO, or are they
Yeah, the problem is we want to be able to update by adding or subtracting elements from the set
without redoing everything?
without redoing it.
Okay.
Yeah, I just ran get UTXO set and it took 1 minute, and then a block arrived and it took another minute.
Okay.
And
Now we
that
know.
would like probably be just like 1 second or so after the block arrives, I have a new hash.
Cool.
So you obviously can't, if it takes a minute to recalculate the commitment for the UTXO set, that's incompatible with having it committed to in the block. I mean, obviously you could commit to the 1, 2 or 3 blocks ago or whatever, but you want it to be fast if you're going to use it as a commitment. So those are 2 methods that Sipper mentioned. Oh. And here's a newer method from Facebook called LT hash.
That's really new.
Is it Libra?
No,
Maybe. I don't
it's
know.
not in Libra.
And again, this uses some kind of homomorphic hashing using some lattice, I think. Another thing I wanted to mention was UTXO. The paper for UTXO came out a couple of weeks ago, maybe a month ago. This is from Taj Dreyer at MIT. And again, this is a commitment to the UTXO set. It's not a consensus change, it's all done on a peer-to-peer level. And what does he say? UTXO is a novel hash-based dynamic accumulator which allows the millions of unspent outputs to be represented in under a kilobyte, small enough to be written on a sheet of paper. There's no trusted setup, because it's hash-based, or loss of security. Instead, the burden of keeping track of funds is shifted to the owner of those funds. So, again, the incentive alignment argument here. With UTXO, the holder of the funds maintains a proof that the funds exist and provides that proof for spending time to the other nodes. These proofs are compact, but do represent the main downside in the UTXO model. They present an additional data transmission overhead which allows much smaller state. UTXO pushes the cost of maintaining the network to the right place. An exchange creating millions of transactions may need to maintain millions of proofs, while a personal account with only a few unspent outputs will only need to maintain a few kilobytes of proof data. UTXO also provides a long-term scalability solution as the accumulator size grows very slowly, with increasing size of the underlying set. So I think the key words here are maintain in terms of the proof. So again, these proofs are not static. They're not. As the blockchain advances, you need to update those proofs.
But these proofs are all algorithmic in the total number of UTXOs?
Pretty sure.
So Taj is going to be here next week, Tuesday through Friday, but mainly in a lightning capacity. And then he'll return later in the summer to talk about UTXO for its own study session, and probably pair that with some of the assumed UTXO work that James has done. So that'll be a little bit later. So we'll learn all about accumulators.
So because this is a peer-to-peer change, you don't need to update all the nodes with new consensus rules, but if you want to be able to take advantage of it, you need to be able to speak this new peer-to-peer language. And so these are UTXO nodes, and these are full nodes, current Bitcoin nodes. And these proofs need to be generated somewhere, and so there are these what are called bridge nodes, which are able to generate the proofs. If this is the end state, if this is what UTXO ends up looking like, and there are always bridge nodes, basically what it's doing is moving the cost of maintaining the UTXO set from this UTXO node onto the bridge node. That's one way of thinking about it. So that's a different security model, right? We're kind of outsourcing UTXO storage.
And just a comment, I'm looking at it, and Facebook's LT hash is based on Belair's paper of collision-free hashing.
Okay.
Like it's not a new research, they just changed the specification of it to be more realistic for real-world applications and made an implementation.
Yeah, thanks.
So the user will be running the bridge node? Who's the
Well,
the owner of the fund?
I might be running a UTXO node, but I can't connect my UTXO node to current Bitcoin full nodes because current Bitcoin full nodes don't know how to send me proofs. So there needs to be some kind of node that speaks both the old PTAP language and the UTXO language.
Can you upgrade? I think your proof changes every block, right?
Yeah.
So can I maintain my? Can I upgrade my proof without like gigabytes of data, or
I believe so. Yeah. I believe if you get given the block, you can update your proof.
So if I just listen, if I continuously listen to the blockchain,
Is that also true for like the TXO bit field system? You said that was the difference with that.
So I think the difference there is because the position in the bit field is unchanging.
Yeah.
The proof is always the same, so you don't need this wallet to be online listening to new blocks.
So you would just need to have the proof for the block in your position in the bit field.
Yeah, I believe so. I think that's the main advantage. Okay. I mentioned this on Monday. Another potential avenue would be to use RSA accumulators. Downside with that is trusted setup because RSA accumulators have like these trapdoors, right? If you know the order of the group, if you know the prime numbers that we use to create that group, then you can insert or remove items from it, or create fraudulent proofs. I won't talk much about that. This is a transcript from a Benedict Wundt's talk at Scaling Bitcoin last year. And then the last one I had in my presentation was Fly Client. I don't know when Lou was going to talk about that, we're running out of time. Some other time. Maybe you can visit over summer.
At the bar at the weekend.
Yeah, it's far later today.
I don't know if you want to give like a 30-second pitch on what that's doing.
The main point of Fly Client is to have lightweight clients that can that don't need all of the linear number of headers from the blockchain. We can instead have a logarithmic number of headers in the size of the blockchain. We do assume there is some commitment to the blockchain in the header, but again, that could be a soft fork as the miners commit to their Coinbase transaction. So that commitment is a Merkle mountain range over the blockchain, basically a Merkle tree with the blockchain, but with the benefit that you added a new block to the Merkle tree in a way that keeps the tree balanced, and that has very little logarithmic number of changes to the tree. So it's really fast to add new blocks to the Merkle tree. And so if you're a light client and you want a proof that some block is the last block in a chain of some difficulty, the prover would return a logarithmic number of blocks from the chain with these Merkle proofs that they belong in the full blockchain. But there's a probabilistic sampling of the blocks in the chain, and this sampling is done using a distribution that we can prove is optimal. So the worst case, because the point is that the adversary wanted to give you a fake proof, try to prove to you that they know some chain that has some difficulty. They would have to know ahead of time which blocks in the chain they would have to fake and do the proof of work for those blocks. So they don't know which blocks you're going to ask for or which blocks are going to be sampled. So it becomes very hard to fake a proof for a chain.
But does this require difficulty to stay steady or continuously rise? But if I can somehow prove to you that the difficulty, actually, like, everybody fell off his miners, difficulty has been dropping for the last few years.
So there is a commitment to the difficulty in the Merkle tree. And that's the part of the proof that we're finishing up is the variable difficulty case. So you also have to verify that the difficulty follows the difficulty adjustment function. Otherwise, there are attacks like the second paper I linked to today in the Slack channel, in which the miner can create these really large fake difficulty blocks and throw out the whole proof.
Any other questions?
So is this as secure as SPV clients right now, like the model they have?
It is, so we adopt, the security model of SPV clients, time with some, it's a probabilistic proof. So you take the SPV clients and then it's whatever security parameter you want and then be your proof. So it's as secure times like 2 to the negative 80 chance of the adversary is lying to you or whatever the security parameter is.
So it is tunable. The more security they want, the more data you need to ask for.
Yeah.
Yeah, Lucia.